To supply 60 amps at 240 volts single phase over a distance of 1200 feet, several installation methods should be considered. Each method has its own cost and efficiency implications. The first option is overhead line installation. Aerial bundled cable, or ABC cable, involves suspending the cable on poles or other structures above ground. This approach is generally less disruptive than direct burial, allowing for easier access for maintenance. However, it can still be more expensive than underground alternatives. Secondly, consider direct burial cable, often referred to as DB cable. This involves burying the cable directly underground, eliminating the need for poles or overhead lines. Direct burial is generally more cost-effective than overhead lines, but it requires extensive trenching, potentially disrupting the landscape. The third option is underground line installation. One approach to underground installation is using an underground conduit system. This involves installing the cable within a protective conduit that is buried underground. This method offers excellent protection from the elements and allows for future expansion or repairs. However, it can be more labor-intensive and therefore more expensive than direct burial. Fourthly, investigate trenchless digging methods. These methods, such as horizontal directional drilling or HDD, bore a path for the cable underground. Trenchless digging minimizes surface disruption and can be more cost-effective than traditional trenching, especially for long distances. Beyond installation methods, also consider other important factors. One critical consideration is choosing between copper and aluminum cable. Copper cable is more expensive than aluminum, but it offers lower resistance and better durability. Aluminum cable is lighter and less expensive, but has higher resistance. Weigh the trade-offs based on the specific requirements and budget. Another factor is proper cable sizing. The cable size must be sufficient to carry the required current of 60 amps and handle the voltage drop over the distance of 1200 feet. Consult with a qualified electrician or cable manufacturer to determine the appropriate size. Transformers may also be necessary. If the power source is not already at 240 volts, a transformer will be needed to step up the voltage to the required level. Remember to factor in the cost of the transformer and its installation. Permits and inspections are also essential. Obtain all necessary permits and schedule inspections to ensure compliance with local codes and regulations. This will help avoid potential problems and ensure safety. Labor costs are another significant factor. Labor costs can vary considerably depending on the installation method, the complexity of the project, and the location. Obtain multiple quotes from qualified contractors to get an accurate estimate. To achieve cost efficiency, you can implement the following tips. Firstly, consider burying the cable in a straight line. This minimizes the amount of trenching or conduit required, reducing costs. Secondly, negotiate with contractors. Get multiple quotes from qualified contractors to find the most competitive prices. Compare the bids carefully, considering both the materials and labor costs. Thirdly, utilize existing infrastructure wherever possible. If feasible, install the cable along existing roads or utility easements to avoid additional costs for new easements. Finally, plan for future expansion. If there is a possibility of expanding the load or distance in the future, consider installing a larger conduit or cable than is currently needed. This can save money in the long run by avoiding the need for future upgrades. When selecting a cable, consider the ampacity requirements and voltage drop calculations to ensure safe and efficient operation. For a 60 amp load, the cable must be rated to carry at least 60 amps continuously. Voltage drop is the reduction in voltage that occurs as electricity flows through the cable. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code, or NEC, provides guidelines for calculating voltage drop and selecting the appropriate cable size. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals 2 times the length of the conductor in feet, times the current in amps, times the resistance per foot of the conductor, divided by 1000. The resistance per foot of the conductor can be found in NEC Chapter 9, Table 8. Once you have calculated the voltage drop, you can determine if the cable size is adequate. If the voltage drop exceeds the recommended limits, you will need to increase the cable size. For example, let's say you are using a 4 American wire gauge or AUG copper cable to supply 60 amps over a distance of 1200 feet. According to NEC Chapter 9, Table 8, the resistance of a 4 AWG copper cable is 0.248 ohms per 1000 feet. Using the voltage drop formula, the voltage drop would be 2 times 1200 times 60 times 0.248 divided by 1000, which equals 35.712 volts. If the source voltage is 240 volts, the voltage at the load would be 240 minus 35.712, which equals 204.288 volts. This is a voltage drop of 14.88%, which exceeds the NEC recommended limit of 3% for branch circuits. In this case, you would need to increase the cable size to reduce the voltage drop. You could use a 2 AWG copper cable, which has a lower resistance. Alternatively, aluminum conductors can be considered for cost savings, but they require larger sizes for the same ampacity and voltage drop performance. When using aluminum conductors, ensure that all connections are rated for aluminum and are properly torqued to prevent oxidation and loose connections. Also, consider the environmental conditions when selecting the cable. If the cable is to be buried underground, it must be rated for direct burial. Direct burial cables are designed to withstand the moisture, chemicals, and physical stresses of the underground environment. If the cable is to be installed in a conduit, it must be rated for use in a conduit. Conduit cables are designed to be pulled through conduits without damage. For overhead installations, ensure the cable is rated for aerial use and can withstand weather conditions such as wind, ice, and sunlight. Furthermore, consider the type of insulation used on the cable. The insulation must be rated for the voltage and temperature of the application. Common insulation types include thermoplastic high heat resistant nylon coated, or THHN, thermoplastic high heat resistant water resistant, or THWN, and cross-linked polyethylene, or XLP. THHN insulation is commonly used for general purpose wiring in dry locations. THWN insulation is suitable for wet or damp locations. XLP insulation offers excellent heat resistance and is often used for high voltage applications. Grounding is another important aspect of electrical installations. Proper grounding helps to protect against electrical shock and prevent equipment damage. The grounding system must be properly sized and installed in accordance with the NEC. The grounding conductor should be connected to a grounding electrode, such as a ground rod or a metal water pipe. Surge protection is also recommended to protect sensitive electronic equipment from voltage spikes. Surge protective devices, or SPDs, can be installed at the service entrance and at individual equipment locations. SPD divert surge current to ground, preventing it from damaging equipment. Consider the available fault current at the service when selecting overcurrent protection devices such as circuit breakers or fuses. Overcurrent protection devices are designed to protect the cable and equipment from overloads and short circuits. The interrupting rating of the overcurrent protection device must be greater than the available fault current. The available fault current is the maximum current that could flow during a short circuit. It can be calculated using engineering formulas or obtained from the utility company. Coordination studies are sometimes performed to ensure that overcurrent protection devices operate in a coordinated manner. Coordination studies help to minimize the extent of an outage by ensuring that the closest overcurrent protection device to the fault trips first. This prevents upstream overcurrent protection devices from tripping unnecessarily. Proper labeling and documentation are essential for electrical installations. All circuits and equipment should be clearly labeled with their voltage, amperage, and function. Documentation should include wiring diagrams, panel schedules, and equipment specifications. This information is essential for troubleshooting and maintenance. Regular maintenance is also important to ensure the safe and reliable operation of the electrical system. Maintenance activities include inspecting cables, connections, and equipment for signs of damage or wear. Connections should be tightened regularly to prevent loose connections and overheating. Equipment should be cleaned and lubricated as needed. Infrared thermography can be used to detect hotspots in electrical systems. Hotspots are areas of excessive heat that can indicate loose connections, overloaded circuits, or failing equipment. Infrared thermography is a non-contact method of detecting hotspots, making it a safe and efficient way to identify potential problems. Power quality monitoring can also be used to identify and address power quality problems such as voltage sags, voltage swells, and harmonics. Power quality problems can cause equipment to malfunction or operate inefficiently. Power quality monitoring equipment can measure voltage, current, and other electrical parameters to identify and diagnose power quality problems. When working with electricity, always follow safe work practices. Wear appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. Energize circuits before working on them whenever possible. Use lockout/tagout procedures to prevent circuits from being accidentally re-energized. Work in a well-lit and ventilated area. Be aware of your surroundings and avoid distractions. Never work alone. Have someone nearby who can assist you in case of an emergency. Following these guidelines will help to ensure a safe and efficient electrical installation for supplying 60 amps at 240 volts over a distance of 1200 feet. Remember to consult with qualified professionals and adhere to all applicable codes and regulations. Consider the environmental impact of your installation. Use energy-efficient equipment and materials whenever possible. Dispose of waste materials properly. Minimize disturbance to the surrounding environment. Educate yourself and others about electrical safety. Promote safe work practices and encourage others to do the same. By following these guidelines, you can help to ensure a safe, efficient, and sustainable electrical system. Remember that this is a general overview, and specific requirements may vary depending on the location and application. Always consult with qualified professionals and adhere to all applicable codes and regulations. In addition to the above considerations, it is also important to consider the long-term cost of ownership. The initial cost of an electrical installation is only one factor to consider. Other factors to consider include the cost of energy, maintenance, and repairs. Energy-efficient equipment and materials can help to reduce energy costs over the long term. Regular maintenance can help to prevent costly repairs. When selecting equipment and materials, consider their reliability and durability. Choose products that are designed to last and perform well over time. Also, consider the availability of replacement parts. Choose products that are supported by a reliable supply chain. Proper planning and design can help to minimize the long-term cost of ownership. By considering all of these factors, you can ensure that your electrical installation is safe, efficient, and cost-effective. Remember to document all aspects of the electrical installation, including wiring diagrams, panel schedules, equipment specifications, and maintenance records. This documentation will be invaluable for troubleshooting and maintenance in the future. Keep the documentation in a safe and accessible location. Update the documentation whenever changes are made to the electrical system. Regularly review the documentation to ensure that it is accurate and complete. Proper documentation is essential for the safe and reliable operation of the electrical system. Consider using a qualified electrical contractor to perform the electrical installation. A qualified electrical contractor has the experience, knowledge, and equipment to perform the installation safely and efficiently. A qualified electrical contractor will also be familiar with all applicable codes and regulations. When selecting an electrical contractor, get multiple quotes and compare the bids carefully. Check the contractor's references and ensure that they are licensed and insured. Ask the contractor about their experience with similar projects. Make sure that the contractor provides a written contract that outlines the scope of work, the schedule, and the payment terms. A qualified electrical contractor can help to ensure that your electrical installation is done right the first time. In summary, several factors influence the most cost-effective and efficient method for supplying 60 amps at 240 volts over 1200 feet. Consider overhead versus underground options, copper versus aluminum conductors, proper cable sizing accounting for voltage drop, potential transformer needs, and all required permits and inspections. Obtain multiple quotes from qualified contractors, explore options for burying the cable in a straight line, and consider if utilizing existing infrastructure is possible. Finally, plan for future expansion to potentially save on costs down the road. Thorough planning, careful material selection, and professional installation are crucial for a reliable and economical power solution.